is what we are discussing. Flow through pipe in downward direction. Okay, flow through pipe in downward direction. We have done a shell balance. In that shell balance, we got this equation: d by dr of r tau rz equals to p0 minus pl divided by l into r. So as r is a variable, so we will not change the location of r. That is very important thing you need to remember. So what is the difference between previous problem and this problem is, here we are getting this is independent variable in the equation. This is dependent variable, you can say. This is independent variable. So as my properties are varying in r direction, so r is there in my equation. So as my properties are varying, I will not change the location of r. That is one difference. Another difference, remaining thing is same thing. And here I have both the pressure forces also and gravitational forces also. Okay, this will be a potential. This is pressure because of external agency, and this is kind of a pressure because of gravitational force. Okay, pressure or potential head. So as it is in downward direction, so this negative sign indicates. So if I am moving in z direction, my potential energy of the fluid is decreasing. If I am moving in z direction, so z direction, with the z direction there is a decrease in potential energy. That is why this negative sign is there. So this is what the difference we got, and most importantly, this difference we got actually. So what difference? This boundary condition we have used, which is called as a logical boundary condition. Logically, sometime, so in a profile equation, logically, so if say tau rz is having some undefined value at any location of at any location in my geometry. For example, here at r equals to 0. If this term remains here and c1, take whatever be the value of this constant c1. So at r equals to 0, this term will give me undefined value of tau rz. So which is not physically possible. It's not physically possible. That doesn't exist. Undefined value of measurable parameter in my system. So undefined value. So it means that there is something wrong in mathematics. There will be nothing wrong in physics. There will be something wrong in mathematics. So it means that, okay, this term should not be there in my equation. Okay, that is what logical boundary condition tells me, that this term should not be there in my equation, and this tau rz equals to delta p divided by 2l into r. This is what we have derived. So if say somebody, if you understood this, whatever shell balance approach, velocity profile, flux profile properly, and you are good in mathematics, so you can put another boundary condition also. The gradient of velocity at r equals to 0 is 0. So if you consider our flow through pipe, okay, so consider this is pipe. So this is my pipe. So this is my pipe, okay, and this direction of flow is here. Direction of flow, this is Vz. What is the value of Vz here? Here roll number 70, Darshan.
Hello?
Yeah, what is the value of Vz here?
So at which point?
This point, this, can you see?
Oh, at the boundary,
Yeah.
it's 0, sir.
Vz equals to 0. And what is the value here?
So here also 0. No slip condition.
Vz equals to 0. And where you are expecting maximum velocity, Darshan?
So at the middle point, at r equal to 0.
So at this point, I will have, at axis, I will have Vz max. Okay. So if I am moving from this point to this point, how this velocity profile will be there? Okay, my velocity profile, if I draw, here I will get maximum velocity. Okay, and then here I will get zero velocity. So you can have, this will be my velocity profile. Everybody got this? This you can, without solving anything, just take out all the information from your problem. This velocity profile you can draw very easily. Okay, now you can see here at r equals to 0, the gradient of velocity equals to 0, isn't it? Because velocity is 0 here, and velocity is maxima here. So I can apply the condition of maxima and minima. So at maxima and minima, the gradient of Vz with respect to r will be 0. So what telling that at r equals to 0, Vz is maximum. So in mathematics, I can say that at r equals to 0, d Vz divided by dr. Okay, this equals to 0, isn't it? Everybody understood this? At r equals to 0, dVz by dr equals to 0, the gradient of velocity equals to 0. And what is tau rz? This tau rz will be equals to minus of mu d Ez divided by dr. So I can take out this boundary condition as this is 0, so tau rz at r equals to 0, tau rz is 0, tau rz equals to 0. This is also a boundary condition, but for that you need a improved understanding. First of all, you should be able to imagine the velocity profile. Then you should have some information about flux profile also. And here this condition, okay, this condition is coming from mathematics. So you should be good in mathematics also. That this condition also you can use here. At r equals to 0, tau rz equals to 0 means C1 equals to 0. C1, so anyway 0 by 0 is also undefined. So directly we may not be so one and same thing at r equals to 0, tau rz equals to 0, hence this term should not be there. That is also one boundary condition I can use. This is clear to everybody. So if you are not, even if you don't know how to imagine the flux profile, velocity profile and mathematics also, then you can use simply, okay, at any physical corner of my geometry, tau rz should not have undefined value. That is what the thing is there. And this term is giving me undefined value at r equals to 0. So at r equals to 0, tau rz is finite. Hence, this term should not be there in my profile equation. Okay. So as this term is not there, so tau rz will be equals to delta p0. Okay, delta p0 minus pl divided by 2l into r. Okay, this will be a flux profile. So if you want to draw the flux profile, this is what my profile equation is there. Flux profile equation. So how this flux profile will be there? Okay, say this is my pipe. Yeah, roll number 1, Abhinav.
Yes, sir.
So how the flux profile will look like?
Sir, it will be 0 at center and
It will be 0 at center
and it will be increasing along R
along R, and where I will get maximum.
at the edges at the.
Okay. So say this is the bottom line. So and it will be increasing. will be increasing. So this will be my flux profile. Is this correct, Abhinav?
Yes, sir. It will be both the sides.
Both the side, because problem is symmetric around theta direction. Okay? So this is both the side. So why I am not showing arrow to this flux profile?
It is tensor quantity.
Very good, excellent. So, so once I got this flux profile, so now I can use Newton's law of viscosity. Okay, Newton's law of viscosity, and you use generalized Newton's law of viscosity, which will be boiled down to this only when Vz is a function of r only. So you can start with a generalized Newton's law of viscosity. Here I'm this here where this Vz is related to you can say location. Vz is related to location. So here we can have velocity profile using this equation where Vz is related to location. It is describing the variation of Vz with respect to r. So substituting this, okay, substituting this and integrating the equation. Now, what is this? This equation is Newton's law of viscosity. Same thing. Newton's law of viscosity. Substituting this and integrating this equation, I will get one more constant. So, it will be a minus. You can say this is a minus. Why minus sign is there? Because I positive direction of r velocity is decreasing. So I am having maximum velocity at the center. If I am moving in positive r direction, velocity is decreasing. So this will have negative value. So hence this will have negative value. A flux tensor, so generally will be represented by positive magnitude only. So positive magnitude, hence it will be minus. So substituting this and integrating this, what I will get? P0 minus PL divided by 4 mu L R square plus C2. Now to get the value of C2, I need a one boundary condition with respect to R. With respect to R of velocity. I need a one boundary condition of velocity with respect to R. At some location of R, velocity should be given. So that is what, then I can get the value of C2 and I can solve and get the value of velocity profile. Roll number 2, Abhishek.
Yes, sir.
So any velocity condition is available here? For,
Yes, sir. At solid fluid interface, no slip boundary condition. At
no slip boundary condition. That is no slip boundary condition. How to define that mathematically?
so at R equals to capital R, VZ equals to 0.
Very good, very good. So so out of this four boundary condition, type of boundary condition in momentum transfer, this is the boundary condition available. This is the boundary condition available. So this is the boundary condition available. So A type, solid fluid interface, no slip boundary condition. As it is a flow of fluid through a pipe, pipe is a solid. So at the interface of solid fluid, the velocity will be equals to 0, and that is at r equals to r. So at r equals to capital R, velocity equals to 0. Substitute this here. So C2 will be equals to P0 minus PL divided by 4 mu L capital R square. Okay, and rearrange the equation. So how to rearrange the equation? So equation will be rearranged such that we should get back our boundary condition very easily. That is what a trick is there in rearrangement. So there can be a number of ways to rearrange the equation. All the time you will be rearranging the equation in such a way that you will get back your boundary condition easily. So it will be you can say you can confirm also whether your profile equation is correct or wrong, or there is something wrong in your profile equation. If you are not getting back your boundary condition, so certainly there will be something wrong in your profile equation. So you rearrange the equation and get the velocity profile. So substitute this r equals to r. Yeah.
So can you go back to that slide where you drawn that flux profile?
Yeah.
Yes. So here in this equation we can see it is also dependent on the length also. So wouldn't it be downwards?
Why it is dependent on length?
So like if the length increases, the tau rz will be decreasing, right?
No. Why it will
So
decrease?
So,
Then,
sir, like, cause
so
it
this
is
is length
divided
of the
between.
pipe. This is not Z. This is total length of the pipe.
Sir, but isn't that length is representing the Z direction only? Like
Yeah,
R is
length is different.
representing the radial direction,
Look,
Z is representing the axial direction.
length is representing Z direction, but I am deriving an expression for particular pipe. This is the length of the pipe. Then if I change the length, it is altogether different pipe. There
Okay,
I will
yes.
get different value of tau Rz.
Yes, sir, yes, sir.
This delta P also change in same way. This
Yes, sir.
delta P also change. So if say you have pump of 1 HP and you are using say some fluid is flowing through pipe, and if here you are using only 1 meter length of the pipe, 1 HP pump, all other thing remains same. So velocity will be certainly different. Now if you are using 100-meter pipe, velocity will be altogether different. So this delta P is also, this is P0 here at the start of the pipe and PL is at the end of the pipe. This is total pressure drop in the pipe. Okay, this total pressure drop is playing a role. This is pressure drop per unit length. So if you
Yes, sir,
change
got it.
pressure also, pressure is also changing with L. Okay, for a particular system, this tau Rz will be constant. So if you change the system, if you change different pipe, then certainly you will get different tau Rz. Okay.
Yes, yes, sir, got it.
So anybody got velocity profile equation? There roll number 6, Aksh.
Yes, sir.
What is velocity profile equation? Your velocity profile equation?
Sir, it is like rho naught minus rho L into capital R square divided by 4 times just divided by 4 times nu L,
This is not a
and
row.
this
This is not a row. This is P.
yes, yes, sir, sorry, sir, rho.
Okay.
Yes,
So
sir,
I
definitely it's
got
pressure, it's
confused.
not
Where is
density.
row actually? Where is row coming in picture?
Sorry, sir, I got it is what it was written in different. So it is P pressure, it is that is
Uh,
what it is. Yes, sir.
this is
So it
measurable
is
pressure. This is measurable pressure, generally
yes, sir.
represented by capital P.
Yes, sir. So equation is, sir, P naught minus PL into R square divided by 4 nu L, and sir, this whole multiplied by 1 minus uh, small r by capital R whole square, 1 minus r by r whole square.
So this velocity profile you might have derived also in, I think, in fluid mechanics, because flow through pipe is a very common phenomena in chemical engineering, and this is parabolic velocity profile you might have derived. That time you have used control volume approach. Okay, that time which approach you have used? Control volume approach generally. Now we are using shell balance approach. Okay, now we are using
Yes, sir.
shell balance approach, and look, here also one hint is there. Sometimes this profile equation will not depends upon a method which you are using. You will get same velocity profile equation, because here there are only two, and this will happen in cylindrical system actually. Why? Because there are only two possible origin, and velocity is not changing in z direction. So certainly you take wherever origin, the profile, so there is only one probability that you will get same velocity profile equation. And you can see here. So getting back this boundary condition is very easy. At r equals to r, substitute r here, capital R by r equals to 1. 1 minus 1 is 0, velocity equals to 0. So easy to get back this velocity profile equation. Similarly, this also, okay, at r equals to 0, so 1 by r is not there, so tau rz is finite value. So this is the flux profile equation, this is the velocity profile equation. Where will be maximum velocity? Maximum velocity will be at the center. At r equals to 0, I will get maximum velocity, and at r equals to r, I will get a 0 velocity. So now, so this is what pictorial representation of velocity profile. This is the velocity parabolic velocity distribution. Vz is a function of r. So this is delta P r square divided by 4 mu L 1 minus r by r whole square, and this is the momentum flux. Okay, momentum flux profile tau rz P0 divided by 2L into r. Now, if I have this, I can get this. Okay, because velocity is related to momentum flux. I can get a gradient of velocity and multiply it by viscosity. Okay, take a gradient of velocity and multiply it by viscosity. So you will get this. So majorly, this is the most important equation in fluid mechanics or momentum transfer. If you have velocity profile equation, you can get a velocity profile, you can get a flux profile, and then once you have this velocity profile, you can get a volumetric flow rate first of all. So you can get average velocity. Average velocity multiplied by cross-sectional area, you will get a volumetric flow rate. So volumetric flow rate multiplied by density, you will get a mass flow rate. Maximum velocity you can get at the center. Just put R equals to R, you will get a maximum velocity. How to get a drag force exerted by flowing fluid on a pipe? So what will be drag force exerted by flowing fluid on a pipe? How to get that value? Here, roll number 9, Nitin.
Hello, sir.
Drag force exerted by flowing fluid on a pipe.
Sir, we multiply surface area with the viscous flux at R equals to capital R.
Very good. So flux at R equals to capital R will be this. This is the maximum flux. Okay. P0 minus PL capital R divided by R. This is the flux at the wall. This is flux at the wall multiplied by flux is nothing but the momentum transfer or shear stress. Shear stress multiplied by surface area. What is surface area, Nitin?
Sir, 2 pi RL.
2 pi capital RL. Okay. 2 pi capital RL, that will be inside surface area of the pipe. So that is what the design important parameter in most of the momentum transfer. Once you have this drag force exerted by, so you can calculate the pressure losses also, you can design the pump or flow through pipes also, and then whatever you can design the support for the pipe using this drag force. You can design the diameter of the pipe and all other thing you can have if you have volumetric flow rate equation, if you have mass flow rate equation and all. So limitation of this theory is, so as the Reynolds number definition is same, dV rho by mu, where diameter is the characteristic length and average velocity is the characteristic velocity. Here it is not based on maximum velocity, it is based on an average velocity, dV rho by mu. If I am using that definition of Reynolds number, then Reynolds number must be less than 2100. This is what we are using. So Reynolds number is less than 2100, flow is laminar, and this is true for laminar flow only because we are using constant density system, okay, and continuous flow. So this is true for incompressible flow. So steady state, we are not considering any accumulation, okay, hence it is true for steady state flow. We are using Newton's law of viscosity, hence it is true for Newtonian, and end effects are neglected. At the start of the pipe and at the end of the pipe, there might be variation in velocity, different velocity. So that we are not considering. End effects are, and near the wall also there might be a different behavior of the velocity because of interface. Interface, it is very difficult to consider that. But anyway, laminar flow is there and that end effects are neglected. So in all, we can assume that all end effects are neglected and there is only one velocity Vz and it is varying only in r direction. These are the limitation of the theory. So now looking at the discussion, whatever we have discussed in this transport phenomena subject, you should be very sure that whenever you are using model equation, you should know the limitation of that model also. That limitation of the theory is as important as that model equation. Just using that model equation, remembering that model equation is not enough. Okay, when actually in real life you are solving any problem, so if you are using any model equation, the limitation of model equation, and then you can judge whether that model equation can be used for whatever case you are dealing with, whenever you are designing anything in future. So limitation is also important. So these are the limitation of this theory, whatever we have discussed, flow through pipe. Okay, and this entrance length, generally entrance length is taken. Okay, end effects are neglected. At the start of the pipe also there will be some disturbances. At the end of the pipe also there will be some disturbances, and this is called as the length till which there will be disturbances. That is called as the entrance length. This entrance length will be a 0.035 diameter into Reynolds number. Okay, diameter into Reynolds number. So L should be very large as compared to LE. At least LE should not be greater than 1%. Okay, entrance length should not be, so L should be at least 100 times larger than LE. Then only I can neglect this end effect. If say my diameter of pipe is 1 meter and my length of the pipe is also 1 meter, so certainly this whole theory will not be good to operate with. Diameter is also 1 meter and length is also 1 meter. So this LE, you can calculate LE and Reynolds number. So it will be very close, and say maybe it will be 25% or 10%. So that time you can assume general, this is thumb rule. So entrance disturbances and exit disturbances should not penetrate more than 10%, 1% of the piping. So that is also one limitation for this theory. So once I have velocity profile equation, I can get maximum velocity. What will be the maximum velocity? Roll number 25. Givas.
Yes, sir.
Maximum velocity?
Delta P by 4UL into R square, capital R square.
Yeah?
Delta P by 4UL into R square.
R square. Okay.
Capital R square.
At how you got this maximum velocity?
At R is equal to 0, we get that.
Okay, substitute R equals to 0. So delta P, P0 minus PL, R square divided by 4 mu L. Then average velocity. This is what average velocity. This will be a velocity average over cross sectional area. So why R is coming? R is coming with d theta. So you go in mathematics and just see how to get the cross sectional area of a circle. So this R, dr, d theta, R varies from 0 to R and theta varies from 0 to 2 pi, will give you a cross sectional area of the circle. Okay, this is what the cross sectional area of the pipe. Circle is the cross sectional area, pi R square. Okay, pi R square or pi by 4 d square. So that this is, say, consider a small differential area dr d theta, and Vz, say Vz is the velocity. So I am summing up this velocity divided by area. Divided by area, this will give me a cross sectional area. As velocity is a function of r, so I cannot take out this directly. Directly I cannot use, say, maximum velocity. So I get me the average value of velocity. Yeah, rule number 38. Dayanand.
Yes,
Yeah,
sir.
what is the value of average velocity?
Sir.
Substitute Vz multiplied by
Yes, sir.
r.
Yes, sir. Doing, sir.
Theta,
Sir,
you can directly take it out because my velocity is not function of theta. Whether velocity is a function of theta, Dayanand?
Sir, no, sir. Velocity is the sir varying with the r, sir.
So why velocity is not function of theta?
Sir, because of symmetry, sir.
Very good. There are only 4 or 5 logical reasoning, but you should remember all this, and you should be very particular. Particular case. Why? So that is very important. So theta you can directly take out. Okay, it will be twice pi, and so
Yes, sir.
multiply your velocity profile equation is z multiplied by r and integrate it with respect to dr and substitute the limit 0 to r. And if you do same thing here, I think here you will get pi r square. This is pi r square. So you can take out d theta here and integrate r. So it will be r square divided by 2, 0 to r. So it will be r square divided by 2. So that is what pi r square you will get here, this integration. So what is average velocity, Dayanand?
Sir, I'm doing integration.
Yeah. Everybody please do the integration. Look, I am not concentrating on mathematics and considering that you are expert in mathematics, and certainly you are more expert in mathematics than me. You know mathematics much more than me. Because just recently you had this M1, M2, so many mathematics, and I have studied this mathematics almost 20 years back. Sayad, Dayanand,
Yes, sir.
did you got the equation?
Sir, I got delta P into R upon 6 mu L pi. Negative minus
I
or
think it
minus.
should be r square.
Sir, I got the RP cube by R square, then R.
So this r square, delta P r square divided by 8 mu L. This is the average velocity. And you mug up these equations actually. This equation for flow through pipe. Flow through pipe is kind of a most important case studied in chemical engineering. And you should know each and everything about this flow through pipe. Okay. So, and this will be equals to half of Vz max. This you can get it from definition of parabola also. If you use the
Yes,
properties of parabola, that time also you will get same thing. Okay. So this will be half of Vz max. Anybody is not getting this equation? Can write in chat box. Anybody else getting this equation? Nobody is getting. Okay. Yeah. So if somebody is not getting this, so just concentrate on this integration and do integration properly. So this is what. And then most importantly for flow through pipe is a mass flow rate. How to get mass flow rate? Mass flow rate, this is the average velocity. Average velocity multiplied by cross-sectional area. That will give you volumetric flow rate. And volumetric flow rate multiplied by density will give you mass flow rate. So this is average velocity. This multiplied by cross-sectional area, that is pi r square. Pi capital R square, that will be a cross-sectional area, that will give you volumetric flow rate, and volumetric flow rate multiplied by density will give you mass flow rate. This is also one of the most important equation in chemical engineering. This is mass flow rate. Mass flow rate will be this average velocity. Okay, first of all, this delta P r square divided by 8 mu L is the average velocity, multiplied by pi r square is a volumetric flow rate multiplied by density. And this name of this equation is Hagen-Poiseuille's equation. Okay, so Hagen-Poiseuille's equation is most commonly used in chemical engineering, and this equation is important in fluid mechanics also, in heat transfer also, in mass transfer also, in reaction engineering also. Everywhere this equation is important, Hagen-Poiseuille's equation. So you should remember flow through pipe. So as previously I told, you should remember all the properties of water first of all properties, density, viscosity, specific heat, this, that, whatever water properties are there, that should be learned by heart to any chemical engineering. Then properties of air. Properties of air, in turn, properties of oxygen and nitrogen. That is also you should know by heart, all the property. And then say in momentum transfer flow through pipe, you should learn this problem by heart. Everything should be learned in detail. So there should not be any confusion in this flow through pipe, because this is also very common example, very common case in chemical engineering. So because even if you are designing the say reactor. So material will be transported to reactor through pipes only, and then you need to design the pump. So even if pumps are used to pump the water, so you need to design the pump. So what is the capacity of the pump? This equation can be used actually. Using this equation, pressure drop and everything. So what is the pressure required in this your reactor and all? So you can design the pump capacity and all. Then you can move on calculation, various design calculations. This is Hagen-Poiseuille's equation, and this is what you will get a drag force. That drag force exerted by flowing fluid on a wall. Okay, this is the total drag force exerted by flowing fluid on a wall. Twice pi RL minus mu dVz by dr. This is estimated at R. This is nothing but tau Rz. Okay, this is nothing but tau Rz estimated at R equals to capital R. You can substitute that, or you can use this velocity profile equation also. You can use velocity profile, differentiate that velocity with respect to R, multiply it with mu, and substitute R, small r, wherever small r is coming, substitute that equals to capital R and multiply it by surface area twice by RL. So you will get a drag force. Okay, drag force exerted by, that will be equals to pi r square delta P. This is correct? Is it correct? Pi r square delta P. Just substitute. So you can use both the way. You can use velocity profile. Use velocity profile and get this equation. Use velocity profile, differentiate the velocity profile, substitute r equals to r, and get the drag force. This is the drag force exerted by flowing fluid on a pipe. So are you getting this equation? You can just comment in chat box. Okay. So what is the importance of this drag force? As I have told so many times. Roll number 47, Gurupreet.
Yes, sir.
Can you tell me importance of this drag force? How we can use this drag force exerted by flowing fluid on a pipe?
Sir, it helps in designing the pipe.
Designing the pipe and
Sir, the pressure exerted by the flowing fluid.
okay. So how it will be help to design the pipe?
Sir, basically it helps us to tell like how much the fluid exerting the force so that we can determine the thickness of the pipe.
Thickness of the pipe. How this will give you thickness of the pipe? Where is thickness of the pipe?
No, sir, it's
How you will calculate thickness of the pipe?
sir in the power calculation we can.
Okay, power calculation. What do you mean by power calculation?
Sir, it's drag force into the velocity FV.
Power calculation.
So P is equal to FV formula.
Look, we are discussing flow through pipe.
Yes, sir.
Flow through pipe. So calculating drag force will help you. How it is going to help you in designing or deciding something.
In designing, sir, support system.
Support system, first of all.
Sir, pumps also.
Yeah, pumps also, very good, very good. This I have repeated so many times. So this delta P you can use in designing the pump. This is what pressure drop is there. Okay, this is what pressure drop is there, and it is related with the drag force. So I can calculate what will be overall drag force, and then accordingly we can decide what should be the capacity of the pump that need to be used to get the appropriate velocity. That is one thing. Another thing is say your pipe is hanging in air, and this will be a drag force exerted by flowing fluid on a pipe. So certainly this pipe will try to move in a direction of flow. So to prevent that, so support should be strong enough. At least it should be more than this force. It should withstand. This is what the force exerted by flowing fluid on a pipe, and then pipe will exert this force on a support. So my support should be strong enough so that it can withstand this much minimum. Okay, minimum it should be this. Then you can design more than that. You can design your support which should be more than this drag force. Maybe you can add factor of safety set at 20%, 50% based on whatever limitation, assumption, whatever fluid you are handling. So how these assumptions are close to your system. So based on that, you can add factor of safety, and then accordingly for that force, you can design the support system. Okay, so this will be equal to, and this you can write. This is, you can say, pressure exerted by a pump only in terms of pump, and this is pressure exerted by a gravity, pressure because of gravity. Just P0, definition of P0. This is measurable pressure. This is pump pressure. This is gravitational pressure actually. So just I will go through this problem once again. So you just slowly go through each and every step if you have any doubt, because I am telling that, okay, the example also I have given. So this is the most important problem in chemical engineering you will come across. Okay, flow through circular tube. So you should learn this problem by heart. So everything should be known to you. Once you know velocity profile, you can do whatever you want, and that too. And still, we are not into laminar turbulent. Anyway, if you are into turbulent flow, then whole of this model equation will not hold good. So altogether, it will be different theory. Okay, there are theory, but based on experimentation, turbulent flow. That we are not covering in this transport phenomena. If somebody is interested, they can read from this, I think, chapter number 7 and 8 in that BSL book, Bird book, chapter number 7 and 9. There, it is all dealing with the turbulent flow, turbulent and complex flow. Okay, so this is flow through circular tube. So this is the definition of total flux we have discussed. Okay, this total flux will be combination of this is molecular flux because of viscous forces, then molecular flux because of pressure forces. This is molecular flux because of viscous forces. This is molecular flux because of pressure forces, and this is the convective fluxes. And then we can substitute all this. Okay, and here we have Vr equals to 0, V theta equals to 0, and Vz is a function of R only, and P is a function of Z. So as there is no velocity in R direction, no velocity in theta direction, so even if you take a theta momentum balance equation and R momentum balance equation, so your input will be equals to output. You are not going to get anything important actually. So we will not consider this balance equation. So important is, okay, important is only a velocity in z direction. Velocity in z direction. So this z momentum balance we will take. So z momentum balance equation. So in that this will be 0, and this is non-zero, and this is non-zero. All other terms are 0, and then we will take a. This is generalized method. Now you can understand this very well. What we have done in two problems. So already we have solved the two problems. What we have done, we have selected the origin, then identify the non-vanishing, and this is generalized method. You can say you can apply it to any equation, any case actually. Write a momentum balance equation. Let the thickness approaches 0. Okay, thickness of the shell approaches 0, and use the definition of differentiation. So you will get a first derivative to obtain the corresponding differential equation for momentum flux. Integrate this equation and get the momentum flux equation. This is flux equation. Then insert Newton's law of viscosity to obtain the differential equation for velocity. Here velocity is related to a location. So Newton's law of viscosity. Then integrate this equation and use appropriate boundary condition to get the velocity profile equation. Say if I don't have flux boundary condition, then without using with the constant, we'll be using Newton's law of viscosity, and there we'll need two boundary condition for velocity. So use velocity distribution. Once I got a velocity distribution, I can get whatever I want. I can get other quantities such as maximum velocity, average velocity, force, drag force on a solid, and so on. So this is what we have done, boundary conditions. So here we have used one boundary condition, solid fluid boundary condition, and another boundary condition we have used a logical boundary condition. This is the case. So this is the flow direction. This is the origin and coordinate system. So this will be our differential shell, because differential thickness will be taken only in r direction, as my properties are varying only in r direction. So this will be a balance shown, and this is the balance. So this is rate of momentum in, this two rate of momentum in, and this is rate of momentum out, and this is the total forces acting in a direction of flow. This is in z direction. Here you can see total gravitational force in z direction. So that will be twice pi r delta r L into rho g. So substituting this and rearranging the equation and using the definition of differential, we will get this. Then we have introduced the Newton generalized law of viscosity, substituted this, and then we have used introduced a modified pressure or measurable pressure. So measurable pressure. So this is d by dr of r tau rz equals to delta p divided by L into r. So this is what the thing is there. Okay. So, and here we will use logical boundary condition. So this term should not be there. As if this term is there at r equals to 0, I will get undefined value of tau rz. So r equals to 0, tau rz is finite. So that will give me this thing. In turn, if you are very good in imagining the velocity profile and mathematics and all, so you can use this boundary condition also at r equals to 0, tau rz equals to 0. Both will give you same model equation for flux profile. Once I have this, I can use Newton's law of viscosity, integrating this equation and using logical boundary condition, no slip condition, another boundary condition, no slip boundary condition. So I can get V at r equals to r, velocity equal to 0, and this is my velocity profile equation. Once I have this velocity profile equation and flux profile equation, so these are the limitations of this theory. I can get maximum velocity, average velocity, mass flow rate, and this is the drag force. So anybody has anything to discuss over here? Everything is clear? Okay, we'll move on to next problem. Just you take down this problem. Okay. We'll discuss this problem in next class, but you take down this problem and take out all the given data. So flow through annulus. Annulus means there are two pipes. So one pipe is having diameter kappa r, kappa is less than 1, greater than 0 and less than 1. So this is smaller diameter pipe, smaller radius pipe, kappa r, and this is capital R. So kappa is between 0 to 1. Kappa is between 0 to 1. So this diameter of the inner pipe is kappa r, and not diameter, radius of the inner pipe is kappa r, and radius of the outer pipe is capital R. And we are discussing flow through these annulus. This is very important when we are discussing a shell and tube heat exchanger. That time this velocity profile is very, very important, kappa. So most important, as I told, flow through pipe. Next to that is flow through annulus. You will come across, okay, because this is there is a jacketed reactor also that can be treated as a flow through annulus and all. So the liquid is flowing upward direction under the influence of pressure and gravity in an annular region between coaxial cylinder. Axis is same of radius kappa r and r. Consider a steady state laminar flow of the fluid with constant density rho and viscosity mu in vertical tube of length L and radius r. Develop the equation for flux profile, velocity profile, average velocity, maximum velocity, mass flow rate, and drag force on a tube. Okay, you take down this problem properly, you note down this problem, think over this problem, and as we have solved couple of problems before, 2 problems before, you start with all 9 components of the fluxes and see what will get cancelled, what is non-zero, and then which flux need to be considered, what should be the shell dimensions, in which direction there will be differential thickness, where I will get maximum velocity, where I will get minimum velocity, what are the boundary conditions which can be used. You just think over this problem. So we will solve this problem in next class. So take down this problem. Take down this problem. Take down this problem and think over this problem. So we will be solving this problem in next class. Yeah, roll number 88. Prathamesh. Prathamesh is there?
Yes, sir.
So how about remaining classes?
About the extra one, sir. Like we
Not
need
extra.
to
It is not extra. Don't call
sir,
it extra class.
we need to
Makeup
reschedule
class.
some.
Yeah.
We need to arrange some classes for the previously missed, no, sir?
Yeah, yeah. Makeup classes. That is makeup class.
Okay, sir.
You have missed the classes.
Yes, sir.
It is not extra class.
Yes, sir. Yes, sir. So, like currently, I cannot promise because the schedule is not yet confirmed for the upcoming week. Like if
Upcoming week means next week is exam, no?
yes, sir. If there are any cancellation of labs or like the lab professor allows us that he'll continue the lab thing after the mid-semester exam, I'll surely give that slot to your class. But if as soon as it is confirmed, I'll inform you personally.
Tomorrow and day after tomorrow will be very good actually.
Sir, we have labs even on Thursday till 7 p.m. We'll be having labs, sir.
7 p.m. You are
Yes, sir.
lab 7 p.m.
Yes, sir. Methekar sir has requested that he'll be taking class on that time.
Okay, Mithikar sir, which lab he is taking?
Mass transfer lab.
Okay.
Today only he confirmed this.
Okay.
So,
okay.
yes, sir. It is going on like today is the first day of the week, so it all starts today from today only. Like as soon as it is confirmed, I will inform you.
Okay. Okay.
Yes, sir.
If you have taken down a problem properly, you have noted down the problem properly, you can leave the class.